Good afternoon, this is Schweitzer and probably a short little video here in our series of acids. I have this one labeled an AP level, not really AP level, just something that I choose to cover to do more in AP. I used it in the last video and it is referring to percent ionization. And a couple of things you might notice about percent ionization is it would be a strong acid would have 100% ionization. Now, ionization means how much has gone through hydrolysis. So HCl plus H2O yields H3O plus Cl minus, initial 0.1, let's say, minus 0.1 down at the equal ending point is 0, gaining 0.1, gaining 0.1. Therefore, I would have an ending pH would be giving me negative log of 0.1 is 1. Okay, that's fine. The Ka value for this guy, well, it doesn't have a Ka value because it's astronomically large. Alright, but the ionization would be the amount that changes, which would be your X value, over the initial amount you have times, might be sometimes deemed the original, times 100 to make it a relative proportion out of 100 equals your percentage or your relative proportion out of 100. So this is going to be 0.1 divided by 0.1 times 100 equals 100%. Okay, that's by definition a strong acid. Now, weak acid. Let's take, for example, okay, let's go with HF. Let's do actually let's do a base here because I don't do a whole lot of bases here, but let's do a base example. So I'm going to do ammonia, which is NH3. That's our typical weak base. There are other examples, but plus H2O yields. Now this is a base, so it's going to accept an H from the water, forming NH4 plus. These two are conjugates, conjugate base pairs. And then we have hydroxide. Initial amount, I'll just go with 0.1. Stoichiometric ratio end, not playing a role. Okay. And then we have 0, 0, minus x, plus x, plus x, 0.1 minus x, x, and x. The Kb in this example, because we're dealing with a base, is going to be x squared over 0.1 minus x. The Kb value for ammonia is 1.8 e to the negative fifth equals x squared over 0.1 minus x. At that point, we'll utilize our shortcut rule here just to make it easier, and I get 1.8 e to the negative sixth equals x squared square root and I get x equaling 0.0013. And you could take the pH of that, no big deal. That's another question. But I want percent ionization. That means I have of my 0.1, 0.0013 times 100 is the amount that ionizes, divided by the original 0.1 times 100 means that it is going to be 1.34%. So in this case, why don't we just go with a 1.3% ionization as opposed to having all this Ka and Kb nonsense. And the reason for that is because this Kb will stay constant regardless of the concentration of my initial substance. But if I were to drop this guy to a 0.01 or 0.001, this thing is only for that concentration. And it will change as I change that concentration. So it's not holding constant all the way along. Let's try an example of that quickly. See, as we have unlimited time here. Let's just do it. Let's go with a point, same thing, initial, stoichiometric ratio, equilibrium. Let's do 0.001. So quite a bit more dilute. Alright, so just following through the math, 1.86 e to the negative fifth, negative fifth equals x squared over 0.001, using shortcut already here, multiply across, and I get 1.86 e to the negative fifth times 0.001, and I get, of course, 1.86 e to the negative fifth equals x squared, square root that previous answer, and I get x equaling 1.36 e to the negative fourth. Okay, now at this point, I get, that's my x value, 1.36 e to the negative fourth divided by 0.001 times 100, and I'm getting, at this point, 13% ionization. So it just depends on the concentration. Okay? So, all right, end of that little tutorial, and we're ready to move on.